Hi everybody, welcome back. Today we are going to be talking about notes 7.3, attributes and transformations of logarithmic and natural logarithmic functions. So here we go. They want us to find the values of x, y, and z given the three exponential functions. So we have 2 to the x equals 4. So what is x going to be? 2 to what power equals 4? If you said x equals 2, you're right. Let's look at the next one. 2 to the y power equals 8. So 2 to what power equals 8? If you said 3, perfect. Let's look at the last one. 2 to the zth power equals 6. Now, is there a power of 2 that will equal 6? Because I know 2 squared is 4 and 2 cubed is 8. So there is no power of 2 that will equal 6. We don't know it. So that's why we mathematicians use a logarithm to find z. So we will end up answering this question during this unit, maybe not this lesson, but maybe in a couple of lessons, and we will figure out how exactly do we find z. So we're going to find the value of z that will, when I raise the 2 to that power, it will equal 6. So a logarithm is the inverse of an exponential. So exponentials and logarithms, they are inverses of each other. Okay, so let's see, how do we convert an exponential into a logarithm or a logarithm into an exponential? So we have the exponential equation to start with. So it says if b to the x power equals y. When we convert that to a logarithm, it looks like this. Now the b becomes a little subscript. So it's log base b of y equals x. So log base b of y equals x. Now, you'll notice that you're going to hear me use a vocabulary term quite frequently during this lesson, and it's called the argument. So the expression that comes between the log and the answer, that little y there, that little y is going to represent the argument. So you will hear me refer to that a lot as the argument. So it's log base of the argument equals x, okay? And some people are like, well, I don't like it in terms of variables. So we came up with something a little bit simpler. We put it in terms of words. So if we're looking at, this is the exponential, it says base to the exponent equals the answer. Base to the exponent equals the answer. That's the exponential. Now let's see how it looks in in logarithmic format. So it's log base of the answer equals exponent. So log base of the answer equals the exponent. So let's think back to exponential functions. So let's think back to exponentials. That's kind of the first two lessons of this unit. So if we have b to the x power equals y, okay? Then we know a couple of things about this. First of all, we know that the b has to be greater than 0 and it can't be 1. So the b has to be greater than 0 and it can't be 1. So b is always going to be positive. That base, that's always got to be positive. So when you change it to a logarithm for the little subscript, you cannot use a negative number. Your base will always be positive. So positive to any power is always going to be a positive answer. Okay, so if I take any positive number and I raise it to any power, my result will always be positive. Therefore, the y, in terms of the logarithm, the y or the answer, that must always be greater than 0. Okay, so let me demonstrate what I'm talking about here. This piece, the argument, So the argument or the answer, that must always be a positive value. Must always, always, always be a positive answer. Okay, or positive value, excuse me. It must always be a positive value. Okay, and then, yeah, so we know base has to be greater than 0. So this right here, the b, or the base right here, that will always be greater than 0 as well. And you also won't have it where it's 1. So just like our exponents, the base is greater than 0, but not 1. All right. All right, let's look at some examples. This says convert the exponential equation to logarithms. You'll notice at the top I've left the rule. Now, you can use whichever version of the rule you like because it's the same thing, but I always use the one with words. It's easier for me. So you pick whichever method you like the best, and that's the one you use. So when we're looking at an exponential problem, we have to identify the base. That's the number that has the exponent. You have to identify the answer. What does it equal? And then you have to identify the exponent. Okay, so right here in number 1, my base is 2 because 2 is what has the exponent. My answer is 16 because that's what it equals. And then my exponent is 4. So when we convert this to an exponential, we get log base 2 of 16 equals 4. Now, the base, that 2, that is permanently attached to the log, okay? I put a little extra space to separate the g and the 2, but the base is attached to the log. So it's log base 2, and then 16 is back up on level, and then it equals the 4, because what it equals now is your exponent. Okay, let's look at number 2. Number 2 is 100 equals 10 squared. So what is your base? Your base is the 10. Okay, the answer, that's the 100, and then the exponent is 2. So this is going to be log base 10 of 100 equals 2. Okay, let's look at number 3. 3 squared equals 9. So my base is 3, my answer 9, and my exponent is 2. So we have log base 3 of 9 equals 2. Now, notice here that we're not solving, we're only changing form. There's nothing to solve for because you don't have a variable anywhere yet. Okay, so this we're just converting from exponential to logarithmic. Let's look at it the other way. Okay, let's look at it the other way. Now you'll notice we're still going to use that formula for converting, but this time we're going from the log to the exponential form. So, same thing, you've got to identify the base, the exponent, and the answer. Now remember, logs always equal the exponent. So, looking at this, I'll identify my base first. My base is 8. My exponent is 2, and then the argument is my answer. So I write this as 8 to the second power equals 64, or 8 squared equals 64. Let's look at 5. So on 5, my base is 2. Okay, my base is 2. My exponent is 3, and my argument is 8. So this will be 2 to the third power equals 8. And lastly, log of 100 equals 2. And you're like, wait a minute, there is no base. There is no base. So let's think about it. What squared gives me 100? What squared gives me 100? Well, that's going to be 10. Okay, so here's the deal. When no base is written, so there is no base, there is, but it's just not written, it's the common log with a base 10. So if we don't write the base and it's not a variable, then your base will always be 10. So this becomes 10 squared equals 100. So again, when there is no base written, it's always going to be what we call the common log, and it's going to have a base of 10. Okay, now we're getting into the fun stuff. We have to evaluate each logarithm. So now you're going to be looking at this, you're going to be like, holy Toledo, Batman, I am now seeing variables. So we're going to show you how to solve a logarithm. Okay? So, same step. Anytime you see a logarithm, you've got to change it to an exponential to evaluate it. So anytime you see a log, you've got to change it back to an exponential to evaluate it. So my base is 9. My exponent is x. And my argument or my answer is 27. So I'm going to write this as 9 to the x power equals 27. Now I know what you're thinking. There is no power of 9 that equals 27. 9 to some power never will equal 27. And you're right. But what base do you think both of these numbers have in common? Think about it this way. What factor, what number does a base of 9 and a 27 have in common? And that answer is 3. So while we can't solve it as it's written, we can change it back to a base of 3, and then you're going to see some magic happen. So 9, that is 3 squared. 27, that is 3 cubed. So this is what it looks like. Now, don't forget the x. Yes, 9 is 3 squared, but 9 to the x power is 3 to the 2x power. Okay? And then, of course, 27 is 3. So you've got to change it back to a common base. Now, if you look here, I've got a base of 3 and a base of 3. Okay, let me think about this. Okay, so if the bases are the same and the left side equals the right side, what must we say about the exponents? And that is that they are also equal. So if you get the bases are equal, then the exponents have to be equal. So we're just going to kind of forget about those 3's. We're going to set those exponents equal. So 2x equals 3. And then we solve for x. X equals 3/2. Okay? So that's pretty much it. So let's recap. You want to convert to the same base. And then you want to set the exponents equal, because if the bases are equal and the left side equals the right side, then you're just going to set the exponents equal. Okay, let's look at number 8. It says 6, the base is 6, so log base 6 of 1/6 equals x. My base is 6, my exponent is x, and the answer is 1/6. So it looks like this. And you're like, well, 6 and 1/6 don't have a common base. Or do they? 1/6, let's remember back to my exponential rules. 1/6, guys, isn't that equivalent to 6 to the negative 1 power? So we're going to pull that 6 up out of the denominator and write him back with a negative exponent. Okay, so if you have your base in the denominator, you can pull it to the top. make the exponent negative, and then now look, we have 6 to the x equals 6 to the negative 1. So left side equals right side, the bases are both 6, so now I can set the exponents equal and say that x is negative 1. Let's look at number 9. Log of, there is no base. But wait, remember if there is no base, it's 10. So log base 10 of 1,000 equals x. So 10 to the x power equals 1,000. Well, 1,000 is 10 to the third. So now we can say, okay, if 10 to the x equals 10 to the third, then x must be 3. Okay, let's prove why y equals 2 to the x power and y equals log base 2 are inverses. Now, when you do this, you want to start with the log because it's easier to work backwards. So we're going to start with the log. So I have y equals log base 2 of x. Now, the first rule of finding the inverses is that you have to do what? You have to switch x and y. That's always the first step in finding any inverse. Switch the x and the y. Now, all you have to do is convert it back to an exponential and solve for y. So we're going to convert from log to exponential. So my base is 2, my exponent is x, and it equals the argument y. So y equals 2 to the x. So, oh my goodness, what I got right here is the same thing as what they gave me up here. And that's what you want it to be, okay? So the first step is we start with the log. First step, switch x and y, and then solve for y. Well, to solve for y, we have to convert it back to an exponential and go from there. And then once you convert it back to an exponential, then you have to just keep solving for y, in which this case we're already done solving for y. But if you had something like y plus 3 equals 2 to the x, then you'd want to move that 3 over if it existed. It doesn't in this case, but once you convert it back to an exponential, if you still have some solving for y to do, you just follow your normal solving steps. Now I will tell you, these problems are not going to show up until part 2. So if you want, you can do your part 1 homework and then go complete the last 4 problems of part 2. You'll see that. If not, you can just do it when you get to the graph for part 2. Okay, let's look at some terminology. First of all, a common log is a logarithm that uses base 10s. We talked about that on one of the other slides. So if you see log of x, that is equivalent to log base 10 of x. We're also going to talk about a natural log. So a natural logarithm is a logarithm that uses base e. So anytime you see ln of x, that's equivalent to log base e of x. Now, log base e of x is not that pretty, so we prefer that you use ln of x. So we prefer, instead of log base e, we want you to say ln of x. It's just it's a more proper form. Okay, let's talk about the calculator. So calculators can only evaluate logs that have a common base, which is base 10. So if your base is something else other than 10, we'll show you in a future lesson how you can use the calculator to do that. But you can only use the calculator right now if your base is 10. Okay? So if your base is 10, you're going to use the log key, the log key. Now, they can also evaluate the natural logarithm. So the natural logarithm, remember, is ln. ln is natural log, okay? And that uses base e. So if you have ln of 5, you can use your calculator. and you're going to use the ln key. All right, let's look at the exponential parent function versus the logarithmic parent function and all of their attributes. So here's our parent function for the exponential. F of x equals b to the x power. Here is our parent function table. And then let's talk about the attributes of the parent exponential function. If you remember, our domain is negative infinity to infinity. Our range was 0 to infinity. There was no x-intercept on the parent function. We had a y-intercept of 0, 1. And our asymptote was y equals 0. Now, given the fact that you know that logarithms are the inverse of exponentials, guess what we're going to do? We are just going to flip-flop all the x's and y's. So here is your parent function for the logarithms. F of x equals log base b of x. So log base b of x. Okay, same thing we looked at back in the part 1 video. So if it's the inverse of b to the x, guess what? Our table is going to just go boop, boop, and flip. So you notice now my x's are 1 over b squared, 1 over b, 1b and b squared. And then you look at your y's, and your y's are the fab 5 of negative 2 to 2. So again, we just flip-flop. So when you're forming your logarithmic parent function, you're just going to go ahead and make your y's negative 2 to 2, and then you're going to populate the x column off of your y's. Now let's talk about domain and range and all that stuff. So domain and range are going to flip-flop. Okay, so if my domain was negative infinity to infinity and my range was 0 to infinity, guess what my domain is going to be for the log? Yep, you guessed it, 0 to infinity. What do you think the range is going to be? You also guessed it, negative infinity to infinity. So remember, when we form the inverse, we switch the domains and ranges as well. Now, on the exponential parent function, we had an x-intercept of does not exist. And we had a y-intercept of 0, 1. So guess what? Now our parent function is going to be the x-intercept of 1, 0. And then the y-intercept on the parent function is going to be does not exist. Now, once we move it up, down, left, and right, we may have a y-intercept, but right now we do not for the parent function. Okay? And then if the asymptote on the exponential was y equals 0, the inverse of y equals 0 is x equals 0. So now we're going to have an asymptote of x equals 0. So exponentials have a horizontal asymptote. Exponentials have that y equals 0. However, logarithms, they have x equals 0. Okay, so just remember, if you can go bloop, bloop, and flip all your x's and y's and everything you know, you're going to be fine. So let's look at the graph of the inverses. Let's take something simple, like f of x equals 2 to the x. So when I plug in, I know that's going to be 1 over 2 squared, so 1/4. Negative 1 is going to be 1 over 2. 0 is going to be 1. 1 is going to be 2. And 2 is going to be 4. Now remember, this is the 2 to the x parent function. This is its parent function. It's not moving up, down, left, right, stretching, and shrinking. Okay, so since this is the parent function, we're going to have a horizontal asymptote of y equals 0. Then we're going to plot our points. There we go. Okay, now the inverse is going to be log base 2 of x. Log base 2 of x. So our y's are going to be the negative 2 to 2, and my x's are going to be 1 over b, which is 2 squared. So that's 1/4. for a y of -1, it's going to be 1 over 2. For a y of 0, it's going to be 1. For a y of 1, your x will be 2. And for a y of 2, your x will be 4. Now, this is the logarithmic base 2 parent function. Now, this parent function right here will only work if your base is 2. If it's base 3, you've got to go create that parent function table. So this table only works if your log has a base of 2. But it's the parent function, so we know that I'm going to have a vertical asymptote at x equals 0. Then I plot my points and connect the dot. See, it looks kind of like a butterfly, which is exactly how it's supposed to look. So we can say that these two graphs are a reflection over the line y equals x. So just remember, since they are inverses, any inverse is a reflection over the line y equals x. That hasn't changed since August, so that's just to remind you of that fact. Okay, so we've talked about b to the x and log base b to the x, but what about e to the x? Well, e to the x is the inverse of ln x. So, you know, when you're trying to get the e's for the continuously compounding interest and all that stuff, you had to go second ln to get the e. That's because e to the x and ln x are inverses and they're on the calculator. Now, as far as log base b and b to the x, on the calculator, you can only do log base 10. So if log of x and b to the x, that's why you do second log to get the b to the x. So that's because both are inverses. Now let's talk about that parent function you had to memorize, because remember the parent function had all these like decimals in it. So that's why we had to memorize the table, and it only made your x's -1 to 2 and your y's 0.41, 2.7, and 7.4. Now, remember we have a horizontal asymptote of y equals 0 on the exponential e to the x function. So we plot all of our points, and there's our curve. Well, it's supposed to be a curve, but that graph tool was giving me a headache. Okay, now let's talk about ln x, though. So remember, ln x, remember, is the same as log base e of x. Now, we want you writing ln x, but that's just a reminder that, oh my goodness, it's just the inverse of e to the x. So, where exponentials had a horizontal asymptote of y equals 0, your ln x is going to have a vertical asymptote of x equals 0. And then to get your ln x table, you're going to take e to the x and go bloop, bloop, flip it, and there's your ln x table. So that's what I was telling you by, if you know your exponentials, you automatically know pretty much the majority of your logarithms. So we plot the points, and there you go. So let's talk about domain and range. Well, the domain on the exponential e to the x was -infinity to infinity, and the range was 0 to infinity. Well, they're going to flip-flop in the ln x, so your domain is going to be 0 to infinity, and your range is going to be -infinity to infinity. Your x-intercept, where the exponential didn't have one for the parent function, your x-intercept is going to be 1, 0 for the logarithmic, the ln x formula. And then this one, you can tell you're not going to have a y-intercept because your asymptote is on the y-axis. So you'll get really close, but you'll never ever touch the y-axis. So on the parent function, your y-intercept does not exist. Now, let's talk about if I wanted the max and min over the closed interval of 1 and 2.7. So what I'm going to do is I'm just going to plug those values in. Because remember, your function is strictly increasing. Okay? So you only have to worry about the endpoints. So if I plug 1 into the function, so if I were to do ln1 in my calculator, I would get 0. But dude, check it out. If x is 1, it's on your table. It's 0. So ln1 is the same as going to your table 1, 0. But just know, okay, just know that when you're trying to find max and min on the calculator, if it's not one of these pretty values, like let's say it was negative, or not even negative, I'm sorry, let's say it was 3 to 7. Okay, so you do ln 3 on your calculator and then ln 7. And then you pick the max and min from those. So you can always use your calculator. So f of 1 equals 0, so ln 1 is 0. And then if I were to put into my calculator f of 2.7, it would tell me, it might not give me exactly 1, because remember the calculator is using that big old version of e. But fn of 2.7, so ln of 2.7 would be 1. You can also balance that off of your table, because when x is 2.7, the y is 1. Okay, so f of 1 equals 0. Well, what is that going to be? Is that going to be the min or max? Well, 0 is going to be the min. And then f of 2.7 is 1, so that's going to be the max. Okay, so we've got the parent functions down. Let's talk about how do we shift it up, down, left, and right, stretch it, shrink it, all that good stuff. Now, I've given you both forms. You'll know that the transformation form of log base b is in terms of a, h, and k. It's the same. It's just the second function is just ln. But a, h, and k affect the log base b the same way they affect ln x. Okay? So, one thing I want to point out, and you need to be really careful when you're writing these equations, because you'll have some where you have to write the equation. So notice here that if it's a left or right shift, you're going to put it in parentheses. Okay, that is super duper important. Okay, that's really important, because if you just write, let's say you go left 7, so you wouldn't say log base b of x minus 7, you would say log base b in parentheses of x minus 7. So if it's a left or right movement, it has to go in parentheses with the x. Now, keep in mind that h's, they still affect the x value, and you always do opposite day. So h's still affect the x's, and you do opposite day. But a and k, they affect the y value, and you just do what it says. You take it at face value. Okay? So, now, when we talk about absolute value of a being greater than 1 and absolute value of a being between 0 and 1, please know that means we just want you to look at the value. So we don't want to go, if it's negative 2 times log, we only want you looking at the 2 because the negative affects it in a different way. Okay? So you take the 2, that does something, and then if it's negative also, that negative does something different. Okay? Just like all of our other parent functions. So if a is greater than 1, so if that a value, again, not thinking about negatives right now, but if a itself is greater than 1, bigger than 1, that means it's going to be a vertical stretch of that value. If just a itself, the absolute value of a, if it's between 0 and 1, that's going to be a vertical shrink. Now, if a is less than 0, so if a is less than 0, that means it's negative. So that negative that's attached to that a, just like always, causes a reflection in the x-axis. Now, h does what h does on any other parent function. It causes a horizontal translation left or right. So if you have minus 7, you would say right 7. Okay? Inside the parentheses, of course. And then k causes us to move up and down, up and down. So that's a vertical translation, meaning you go up or down. Okay? And then remember, we can use a, h, and k, or if you like a, c, and d, that C and D are the same things as H and K, so it's your preference. All right, let's talk about how transformations affect the other attributes of my function. So we know in the parent function, the domain is 0 to infinity. Now, on the transformation function, remember that that function and the asymptote move as one. It's like there's a magnetic connection between them, okay? So if the function moves right or left, the asymptote goes that way as well. So what affects our left and right movement? The h value. So our domain is going to be h to infinity, okay? Now the range, negative infinity to infinity. Now we all know that's not going to change if we go up, down, left, or right. It's still going to be negative infinity to infinity. So on the parent function, we have an x-intercept of 1, 0. To get the x-intercept in the transformation function, we're going to have to plug in 0 for y and solve that logarithm. Okay, so you'll plug in 0 for y and evaluate the log. Now, on the parent function, we know we don't have a y-intercept. But on the transformation, we may have one. It just depends on the equation. So if your equation goes left, you're going to have a y-intercept. But if it goes right, not going to have a y-intercept. And then this says your parent function has a vertical asymptote of x equals 0. Well, remember if you move left or right, that asymptote's going with you. So your vertical asymptote is x equals h. X equals h. All right, let's look at this and see how we do it. Okay, let's actually graph one of these guys, okay? So y equals log base 2 of x plus 1 plus 4. So let's talk about the horizontal shift and the vertical shift first. So horizontal, x plus 1, well, remember that's really opposite day, so we're actually going left 1, okay? And then we have a plus 4. Well, that's taken at face value, so that means we're going to go up 4. So let's talk about how we graph this down. Well, just like remember with the exponentials, we had to create the parent function table. Same with the logs. You have to complete the log parent function before you go up, down, left, and right. So log base 2 of x, remember our y's are negative 2 to 2, and now our x's are 1 over b squared, 1 over b, 1, and b squared. So my b value, my base, is 2. So 1 over 2 squared is 1/4. 1 over b, 1 over 2. 0 is 1. 1 is 2. And then 2 is 4. Okay, so I've got my logarithmic parent function. Now I'm going to create the transformation table using our equations they gave us. So it says x plus 1, but remember it's opposite day. So instead of adding 1, you're going to subtract 1. So 1/4 minus 1. Let's see, if I have a quarter and I owe somebody $1, I am short 75 cents. So I am negative 0.75. Okay, and if you want to use decimals, that's okay to graph your table. Okay, so 1/2 minus 1. Well, if I only have 50 cents and I owe somebody $1, I am short 50 cents. 1 minus 1, well, that's 0. 2 minus 1 is 1. 4 minus 1 is 3. Okay, so we've done our left and right movement, our horizontal translations. Now let's talk about our y values. How do I go from old y's to new y's? Well, I'm going to add 4. So negative 2 plus 4 is 2. Negative 1 plus 4 is 3. 0 plus 4 is 4. 1 plus 4 is 5. And 2 plus 4 is 6. Woohoo! Okay, so I have my transformation table. But before I do that, I need to determine what is my vertical asymptote. So if you remember from the previous slide, it says that your vertical asymptote is x equals h. Well, my h is -1. Okay, so that means I'm going to have a vertical asymptote of -1. There we go. So there's my vertical asymptote. Now we're going to plot our points. And then we're going to connect the dots. Now we're going to get right up super duper close to that asymptote, but we are not going to touch it and we're not going to cross it. So let's talk about domain, range, x-intercept, y-intercept. Okay, so the domain, that's h to infinity, h to infinity. So it's going to be -1 to infinity. My range, well, that's going to be -infinity to infinity. My x-intercept, if you look at your table, you don't have any y values that are 0. So I'm going to show you the work for that on the next slide. So hang chilly, we're going to go do that, find the x-intercept on the next slide. So the y-intercept we do have, that is when x is 0, and we do have that on our table, and it is 0, 4. Now, if you didn't have the y-intercept, you could plug 0 in for x, evaluate that, and go from there. Okay, so how do we get the x-intercept on the previous slide? Well, anytime you want to find the x-intercept, you let y be 0. Okay, that's pretty straightforward. Now we've got to evaluate this logarithmic. So, and solve for x. Now here's the deal. This stays all together. Okay, that stays all together. So we need to move that 4 to the other side because he is not permanently attached to the logarithm like the base and the argument are. So to undo addition by 4, we're going to subtract 4. So I get that -4 equals log base 2 of x plus 1. Now, once we've got the log and the argument isolated, once they are isolated, then we change it to an exponential. So that becomes the base is 2, the exponent is -4, and the answer is x plus 1. Okay, so base, exponent, answer. So that's why we taught you that before. So 2 to the -4 is 1/16, because remember that's 1 over 2 to the 4th, and 2 to the 4th is 16. So that becomes 1 over 16. Now I subtract 1. So 1/16 minus 1. Now remember, 1 is technically 16 over 16. So 1/16 minus 16/16 is -15 over 16. Now remember, we can't leave it like that. You've got to write it as a coordinate point. So you're going to write that as -15 over 16, comma 0. All right, let's do an LN graph. So let's talk about the movement. X minus 1, well, that's right 1, plus 3, that's up 3, and then that 2 in front, that's going to cause a vertical stretch of 2. Okay, so we've talked about the movement, right, up, and vertical stretch. Now let's talk about graphing it. So we know our LN table is just the inverse of the e to the x table. So this time my y's are going to be -1 to 2, and my x's are 0.4, 1, 2.7, 7.4. Now we're going to do the transformation equation. So to go from old x's to new x's, I have to add 1, because remember, it's opposite day when it comes to the x's. So I'm going to add 1. So 0.4 plus 1, 1.4. 1 plus 1, 2. 2.7, 3.7. 7.4, 8.4. Awesome. Now we're going to do the transformation from old y's to new y's. So to do that, remember, we multiply by 2 and then we add 3. Remember, we always multiply before we add or subtract because that's what PEMDAS says. Okay? So 2 times -1 is -2 plus 3 is 1. 2 times 0 is 0 plus 3 is 3. 2 times 1 is 2 plus 3 is 5. And then 2 times 2 is 4 plus 3 is 7. Excellent. Now we've got the points for our graph. But remember, we have to do the vertical asymptote first. Okay? So remember that's x equals h. Well, in this case, h is 1. So our vertical asymptote is going to be x equals 1. Zoop, there it is. All right, now we're going to graph our points. Excellent. Let's talk about domain, range, y-intercept. So my domain is h to infinity, so that's going to be 1 to infinity. My range, still going to be -infinity to infinity. My y-intercept, I'm not going to have one this time because my asymptote is at x equals 1. So I'm never going to get close to that y-intercept. Now let's talk about how I get the x-intercept on the previous slide. So remember, that means set y equal to 0. And we also have to isolate this part. We have to isolate the 2 ln of x minus 1. So to do that, we've got to kick the 3 to the other side. And then, remember, we really have to get rid of the 2 as well, because really this is the only part we're looking at. So we divide by 2. So I get -3 over 2 equals ln of x minus 1. Awesome. Now you're like, well, how do I figure this out? Because ln doesn't have a base. Or does it? Let's look. Remember, ln is the same as log base e. ln is the same as log base e. So to convert this back to an exponential, we're going to say e to the -3/2 equals x minus 1. Now, when you're entering this in your calculator, you're going to do second ln, and then you're going to put that exponent in parentheses, -3 divided by 2, close parentheses, okay? But to solve for x, we know we're going to have to add 1. So, again, going back to my calculator, we're going to do second ln to get that e. Then in the exponent place, we're going to open up a parentheses. We're going to say -3 divided by 2, close parentheses, plus 1, and that's going to give us our answer of, and we rounded to 1.22. So if the directions don't say what to round to, 2 places is generally what we do. But remember, we can't leave it like that. We have to write it as a coordinate point of 1.22, 0. Now, let's talk about finding the maximum and minimum of y equals 2 ln of x minus 1 plus 3 over the interval 3.7 to 8.4. Okay, so what we're going to have to do here is, remember, it's consistently increasing, so we're just going to plug in the endpoint. So we're going to do 3.7 first. So 2 ln of 3.7 minus 1 plus 3. Well, 3.7 minus 1 is going to be 2.7. Now, at this point, you can jump into your calculator, okay? It's calculator time. So you'll enter it just like it looks. 2 ln, you don't even need a multiplication sign between 2 and ln. The calculator knows. So 2 ln, open parentheses, 2.7, close parentheses, plus 3. Those parentheses are so important, okay? So when I do that, I get 4.99. Now let's try 8.4. Well, 8.4 minus 1 is 7.4. So again, calculator time. So again, 2 ln open parentheses, 7.4 close parentheses, plus 3, and we get 7 right on the dot. So 4.99, that's going to be my minimum. 7.00, that's going to be my maximum. Okay, so pretty much from here, we're just going to be practicing solving the logarithms. If I were you, I would make sure that I go through every slide, so don't stop the video here because we are going to have lots of different examples that you may see for solving. So hang in there with us and keep going because there's all sorts of different solving out there. So we want to make sure we cover as many cases with you as possible. Okay, so express 2 to the 4th equals 16 in logarithmic form. So here we're not evaluating the logarithm, we're just changing form. That's all we're doing, we're just changing form. So I need to know my base, my answer, and my exponent. So my base is going to be 2. My argument or answer is going to be 16. And my exponent is 4. Did you say log base 2 of 16 equals 4? If you did, pat yourself on the back. Okay, what I want you to do here is stop the recording, stop the video, and see if you can convert this to logarithm form. Okay, let's see how you did. Again, we're not solving, we're just changing forms. I got log base A of C equals B. How are you doing? Okay, let's look at this one. Now this one wants us to change from log form to exponential form. So pause the video and see if you can tackle this one. Did you get A to the Cth power equals B? If you did, pat yourself on the back. That's awesome. Let's move on. Again, here, just to reiterate, we are not solving. We are only changing. Okay, here's another one. Pause the video and see how you do. Did you get 3 squared equals 9? If you did, congratulations. Okie dokie. Now we're into evaluating. We're going to evaluate. You're like, well, it doesn't equal anything. Well, if I say evaluate log base 2 of x, if we don't know what it equals, what do we make it equal? That's right, we make it equal x. So now remember, to evaluate a logarithm, you have to convert it back to an exponential. So what would this be if I converted it back to exponential form? It would be 2 to the x power equals 8, because my base is 2, my exponent is x, and it equals the argument, or it equals the answer, which is 8. Now, again, you know, here you, I mean, we pretty much know x is 3, but that's not showing your work. So yes, we know 2 to the x power equals 8. We know x is 3. But again, you've got to show your work, because remember, now you're submitting your work. So we're like, well, how do I solve? Oh, wait, I can change this into common bases, right? So what is the common base between 2 and 8? Well, the common base is 2, because 8 is 2 to the 3rd. Now that base equals base, exponent has to equal exponent. So x equals 3. Let's do another one. Okay, let's try this one. Evaluate log base 1/2 of 8. Now, it doesn't equal anything. So if we don't know what it equals, we make it equal x. Okay, so remember, we have to convert a logarithm to an exponential. So my base is 1/2. My exponent is the x, because the exponent is what the log equals. And then that equals the argument or the answer. So this gets changed to 1/2 to the x power equals 8. Now, you're probably sitting back going, I don't really see a common base there. Now, let's think about this though. 1/2 is essentially a power of 2, and 8 is a power of 2. And you're thinking, wait a minute, go back. How is 1/2 a power of x? Well, that 2 is in the denominator. But what if I move him back up to the numerator? He goes from being 2 to the positive 1 to being 2 to the negative 1. So 1/2 x is 2 to the negative 1x. And then 8 is 2 to the third. So 2 to the negative x equals 8. And 8 is 2 to the third. Now, you're probably wondering, oh my gosh, do I have to show that step in pink? No, you don't. You could, if you realize that, you could go from the blue to that purplish color. You could go from 1/2 to the x power equals 8 to being 2 to the negative x equals 2 to the third. I just showed every step along the way. Okay, now that the bases equal the bases, then that means the exponent has to equal the exponent. So that becomes negative x equals 3. Well, we got to solve for x. So we divide by negative 1, and I get x is negative 3. Let's try another one. I want you to try this one on your own. So stop the video for a second, see if you can solve it, and then hit play when you're ready to check your answer. Did you get x is negative 4? Perfect. Let's have you try this one. 3 to the x power equals 1/9. So pause the video and see if you can solve it on your own. I got x is equal to negative 2. Did you get that? Ooh, this one's going to be super fun and challenging. Okay, so we have 2 to the x plus 1 power equals 1/16. Okay, and you're thinking, 2, well, 16 is the power of 2, but it's in the bottom. Okay, it's in the bottom, so, but I can express 16 as 2 to the 4th, right? So 2 to the x plus 1 equals 1/2 to the 4th. But they have to be on the same level, so I need to send that 2 to the 4th up to the numerator. Well, he's crossing that fraction bar, so he goes from positive to negative. So that becomes 2 to the x plus 1 equals 2 to the negative 4. Now, base 2 equals base 2, so that means exponent needs to equal exponent. And now we solve for x. I subtract 1 from both sides, and I get x is negative 5. Let's look at this guy. 3 to the x power equals 27 squared. And you're like, dude, holy Toledo Batman, I am so done. I'm so over this. It's not that bad. 3 and 27 are both, what's their common base? What's their common base? Well, 3, right? Because 27 is the power of 3. So the left side stays the same, but I'm going to express 27 as 3 cubed. Okay? Now, here's where you've got to be really strong in your exponent rules. If I have one base to an exponent that's to another exponent, that's the power of powers. One base, two exponents, we multiply. So that becomes 3 to the x power equals 3 to the 6th. Now, base 3 equals base 3. So x has to equal 6. Ooh, okay, like this one is kind of my favorite. I'm not gonna lie. I love these problems. I just love exponentials anyways. But okay, yeah, I know, I'm a nerd. Get over it. Okay, so let's look at this. 2 to the 8x equals 32 to the x plus 2 power. Now, you have to ask yourself, what is the common base between 2 and 32? The common base between 2 and 32 is 2, because 2 to the 5th is 32. So we got to change it so that they are in the same base. Now, here's where you really need to be super duper careful when you're cleaning up these exponents. So right here, this is a 5. So I'm going to multiply 5 times x plus 2. But don't forget, you've got to distribute. I guarantee you guys, 99% of the problems that happen on a problem like this is you don't distribute the 5 to the x and the 2. That's not going to become 5x plus 2. It's going to become 5x plus 10. So please, please, please be super careful about that, and remember that you have to distribute that single exponent to the other two if it's a binomial. So okay, we now have 2 to the 8x equals 2 to the 5x plus 10. Base 2 equals base 2, so 8x has to equal 5x plus 10. Then you solve like normal. You bring the 5 over, which gets you 3x. 3x equals 10. You divide by 3, and we come up with x equals 10 over 3. Ooh, this one's good too. This one is awesome. So I've got x to the negative 3 equals 8 over 27. Now you want to make sure that you really pay close attention to this, because this is a really cool problem, okay? So you have x to the negative 3. Well, can't have negative exponents on a variable, so you convert that to be 1 over x cubed. Now, we have a rule that says, because you're like, ooh, I don't want that, that's going to be hard, I don't want to cross multiply and solve. You don't have to cross multiply and solve, because we have a rule that if you flip the left side, you have to flip the right side. As long as you flip both sides, the fractions are still equal. So I'm going to flip that to be x cubed equals 27 over 8. Okay, so then I say, okay, well, this one's not where we can get the same base. But what if we got the exponents equal? What if I said this to the third power equals this to the third power? Oh my gosh, 27 and 8 are both perfect cubes, right? So can I say that x cubed equals 3 halves cubed? So using our same argument, just a little bit different, if the exponents are equal and the left side equals the right side, then the bases also have to be equal. So x equals 3 halves. Okay. Let's look at our next example. They want us to solve for x. Our problem is 1/3 to the xth power equals 81. The first thing I want to determine is, can these both be changed to the same base? 1/3, 81. Well, they're both powers of 3. 1/3 is 3 to the negative 1. 81 is 3 to the 4th. So I do that first. I change them so that they're in the same base. Now, on the left side, I have a power of a power. So I have one base, two exponents. So I need to fix that. I multiply the two exponents together. So now that they are both powers of 3, the left side equals the right side, I can now set my exponents equal. So negative x equals 4. I divide by negative 1, and I get x is negative 4. All right, let's look at this one. Why don't you pause it here and see if you can write the transformation. Okay, so that x minus 1, that's going to be right 1, and our minus 5 is going to be down 5. All right, what is the domain of the graph log base 3 of x minus 1 minus 5? Now remember, your domain is h to infinity. So my h is 1, so 1 to infinity. Okay, let's look at our last example. It says, what is the x-intercept of the graph f of x equals log base 3 of x minus 1 minus 2? Well, the x-intercept is where y equals 0. F of x and y are the same thing, so I'm going to substitute in 0. Now I have to get the log completely by itself, which means I need to undo subtraction by 2 so that I can move it to the other side. So I'm going to add 2 to both sides. Now I'm going to change it to an exponential. So I have 3 to the second equals the argument x minus 1. So 3 squared equals x minus 1. 3 squared is 9. 9 equals x minus 1. I add 1 to both sides, and I get 10. So therefore, our x-intercept is 10, 0. All right, that concludes it for this lesson. You are now free to go work on your worksheet 7.3. Please remember to wash those hands, wear your mask, socially distance, use hand sanitizer, stay 6 feet apart, and make good decisions. All right, and we will see you guys back for the next lesson. Have a good one. Bye.